studied so far is going to be kind of repeated again in a way, because from the textbook also will say the same thing, right? So good morning, Jamila. So I have it. No problem. So put yourself on mute, you know.
Sorry, I thought you're on mute.
Yeah, I got in the mute. Yes, sorry for. I think I've muted myself from there actually. So okay, so I'm clicking on the record button. I already clicked on the record button. It's going to be recorded on my computer. So you see my recording, right? So I'm going to share my screen with you. So File Explorer. I'm going to the File Explorer. And then the documents. And desktop. And I have my courses here. Operating systems, lecture notes, the last topic here, which is the main memory. I'm going to bring the XP pen in 1 minute. I'm sharing my screen with you. So putting myself on mute for 1 minute. So back again. So let me just open the video. So you see me now, no problem. So let's start working on the topic. I'm just moving it away here, making it bigger to this, minimizing this one, right? Okay, all right. So main memory here, right? Look at the main memory. So you will see the algorithms that we looked at it again, you know, from the perspective of the textbook. So background memory, main memory is a very, very important topic. You know, without knowing main memory, you can't do programming, you can't do anything. You know, so understanding main memory helps you. You know, you can work with the computers without even knowing anything. We all know it. A lot of people have been using the computers. So using computers is not a big deal because most of the time the you know, you will be using only applications which are supported by the operating system in the back of the you know, applications. Your front end interface is always the application. All that you need to do is operating system interface is double clicking or, you know, single clicking, double clicking, that kind of thing from the, you know, from the foreground. So which is like anybody can do that. So it's not that you need a, you know, operating system knowledge to be able to operate a computer. Okay. So, and that being said, main memory, you being a professional in computer science, memory management is the most important topic. And CPU is as much important. Memory is that much or even more important. And, the device management is also very, very important. And it all linked to the main memory anyway. So swapping, so virtual memory, memory can be RAM, memory can be so many different types of memory, right? Even a register is a piece of memory. Cache memory, RAM memory, RAM extended on the disk is a virtual memory. And, you can also say that is, disk memory and, tape memory. Even a paper tape is a memory. You see what I mean? If something you write on a piece of paper, is still memory. And you know that in the old times, there used to be a paper strip. I probably did not even see. The punch cards is also memory. So punch cards are stored. A paper tape like with holes in there, like that. You know that? You probably never saw it. The paper.
I guess I already saw in a movie
The movie.
the old IBM computers.
Yeah. So the punch
They have
cards,
cards.
these are cards. And you have, I think the punches, the punch card, you punch it, A, B, C, D, and it punches appropriate the whole,
Logins.
strip, yes, yeah. So not markings, actually, it puts a hole in there. Really puts a hole in there.
Use it for logins, I guess.
Yeah, but this one is a paper tape, really paper tape. And then I used to keep them, paper tapes. Once you actually, paper tape is much efficient than the punch cards. Okay, anyway, tape memory, paper tape memory, magnetic tape, and even this paper tape. Contiguous memory allocation algorithms, segmentation, paging, structure of a page table. Okay, we will see that again and some of the examples. That's all you're going to study in this topic. So various ways. I think, did I complete some part of it? Not yet, right? So I think I gave you only this one. So we didn't go formally. I think I went very quickly. So there are various ways of organizing the memory hardware. So memory management techniques, including paging and segmentation. So, and then we are going to see some of those implementations in the Intel Pentium, which is supporting pure segmentation and also, segmented pages. So you have program must be brought from the disk, right? The program is on the disk, right? And it becomes a process in the memory, right? So main memory, okay, and registers, okay. So the storage, CPU can access directly the main memory and, and the registers. The CPU can access directly. What about the other memory, which is like a disk memory or tape memory? How do you access? CPU doesn't access directly. How does it access? Via a device driver, right? Isn't it? There's a driver for each, disk driver, tape driver. So the driver is a program that allows you actually connects, the CPU to the direct, give a command, we give a command based on your, operating system is going to give a command, and then you will be able to actually, a device driver is going to bring things onto the, memory, and then you will be able to use it. So bringing this, main program to the memory is from the disk anyway via device driver. So every device like a disk or, anything, a tape will have a driver. So, and stream of addresses, right? Basically memory is nothing but addresses. So every byte has an address, right? Unique address. So read request and the write request for the data, whatever, right? So register accessing one CPU clock cycle, right? One CPU clock, or even less. I think this one is the minimum anyway. Okay, register access. What is CPU clock? Can anyone tell me, please? What is the CPU clock means?
The frequency.
Yeah, the frequency, the number of cycles per second. In 1 second, how many? For example, 3 gigahertz is my speed of my computer. So 3 gigahertz. So which means that clock tick equals to, okay? So 1 over 3 multiplied by 10 to the power of 9 seconds. So which is 1/3, like 0.33, 10 to the power of minus 9 seconds. So 1/3 of a billionth part, right? This is 1/3. And this is billionth. You take, 1 second and divide it into 1 billion. 1 billion. And you take one of it, of the 1 billion, and make it 1/3. And that's what the time is. So tiny, right? Isn't it? So tiny. So that is a CPU clock tick. CPU clock. One CPU clock tick, I should say clock tick there. So CPU clock cycle or, tick. One tick is amount of time. Just like you take your wristwatch, you have, seconds needle is moving 1 second at a time. But this one is going not just a second. So 10 to the power of like you take 1 second and divide that into 10 to the power of 10, like 3 parts of that. 10 to the power of 10 ticks, right? 10 to the power of minus 9 means, look at it, how small it is. Okay. So main memory can take many cycles, like a memory access, like it takes much more cycles, right? Register access is fastest, and the cache is the next fast. So cache is the next between the CPU and the CPU registers and the main memory. So people write programs in the CPU registers. I used to write always the CPU registers directly. So program. So assembly language lets you actually directly deal with the registers. Protection of memory required to ensure correct operation. Okay, basically memory should be protected, right? That means no one else is going to step on the memory. So a pair of base and limit registers define the address space. So there are 2 registers which are very important registers, which is a base register and a limit register. For every process, you have a base register and a limit register. Every process is given. So which means that you take this process, for example. Okay. So obviously the base register will point to this address. So the base register is holding this address. That's the beginning of that process. And from there, the size, size of the process is this one. This is the limit register. Okay, any address should be between them, which means that the first address is this one. Okay, the first address is byte and the last address is this byte. Okay, both are included. Okay, how many bytes are here? These many bytes are here. You understand me, right? So how do you actually get it, sir? So you subtract 3,000, like, 1,040. You write that and then add 1 to it, right? Isn't it? Why add 1 to it? Because it's 0 relative. Do you agree with me? You take 1 byte, for example, it will be at 1200, 120909. So that's 1 byte. Okay. So that's why you actually have to add 1 to it, right? So it becomes exactly like you get the number of bytes. Yes or no? So basically what you do is you you take, for example, 120, 900. So 120, okay. So 901 is 2 bytes actually. So if you subtract it, you will get only 1. So you have to add 1 to it. Okay, all right, you understand, I hope. I think I already talked about it. It's a repetition. You're taking any address that is going to be accessed, right? Should be greater than the base register or equal to base register, and less than. When you add them together, it should be less than. It's not less than or equal to. You want to put less than or equal to. Okay. So it should be -1. -1, because then it will be less than or equal to. Okay, all right. So address binding. It's very important that address should be within the So program on the disk is ready to be brought to the main memory. Execute a input queue. So that means you're maintaining a queue of programs that need to be brought to the main memory, right? Okay. So without that support, must be loaded into the address 0. Address 0, where is it actually? Operating system is living in it, right? So somebody got to actually put its process in the right place. So you cannot have every process sitting down at the same place. Obvious, right? I think you shouldn't even write this. So any address should be actually, what he's saying basically, your program is always relative to 0. The address is 0 for your program. Whereas when it is loaded into the memory, so it's not the same address. So it's called a relocation. You're binding to relocatable addresses, right? Okay. All right, relocatable address, absolute address. So relocatable address, relative address is then relocatable, right? Compile time, what you get is you compiling, linking, and creating an executable module, right? And that is absolute addresses. So are generated at that time starting from 0, right? And the load time, you're relocating the code into the main memory somewhere in the memory, right? Isn't it? So that's the load time you're loading. At execution time, you are actually finding out your actual addresses for each instruction, right? You are doing that math thing and then trying to actually find out whether your program is correctly loaded and so on. If you have any question, please stop me, right? So compile or assemble. So why you say or assemble? Compiling or assembling is the same kind of job. Converting the source code to object code or executable code. Okay, this is the executable code. So one program, another program, another program. So all executable codes should be linked together to create a loadable module. Okay. For example, one program is starting from 0 to 49. Okay. Another program is again 0 to 49. 0 to 49 is 50 bytes. So 0 to 49 is 50 bytes also. When you link them together, it will be a load module, which are executable module, right? So load module that is starting from 0 to 99. So this is 100 bytes. 0 to 99. 100 bytes you have. So, you're putting them together into one piece. Okay. So when you are compiling, each one is relative to 0. But when you link them together, you're putting them together. So now it's going to put that in the memory. It is going to be loaded in somewhere in the memory. Okay. And again, you're loaded. Not only you're loaded, but also, there are some, linkage modules for you. Libraries. Okay. So libraries in the system are dynamically loaded also. Okay. So we'll see it exactly when it comes to. So let's system library. So logical address is the process address, right? And a physical address is the RAM address, We've been saying all the time, logical address space is generated by the program. Okay. So whereas that is zero relative. And this one is base register relative. This is a base register relative. Okay. So hardware device. Okay. At the runtime, you are mapping the virtual address to physical address, right? So memory management unit, MMU. There is a program. This is a program in the operating system. MMU is, one piece of code, right? So it always works on the memory management. So several methods are possible for, we are going to look at it. So, okay, simple scheme. So relocation register. Okay, base register. There are 4 relocation registers in 8086. 80X means 186, 286, 386, 486. This is the original Intel chips before Pentium 4. And Pentium 4 is the first modernization. And then, today you have, more powerful, the processors, right? Okay. So user program deals with the logical addresses. Okay. And, never need to worry about the real physical address because it's not loaded there. So how can you think about physical addresses without being loaded? So execution time, you need to binding the memory, the logical address to physical address, right? Conversion. All right, sir. So if your logical address is 346, for example, which is relative to 0, right? And then your relocation register is 14,000. And then add them together, you get the physical address. And you go to the memory and fetch it. Okay. All right. Any questions you have? 1 second. Okay. All right. So DLL, so dynamic, relocation or dynamic link library or so DLL routine, which is actually, library files or something, right? So you're using relocation, routines, not loaded until it is called. So at that time, you will be actually loaded. So better space utilization because it will not be loaded every time. So it will be actually, so relocatable load format. So using large amounts of code is needed, So infrequency of, because you don't use them all the time. So there's a lot of libraries which don't use them as you load them. So sometimes you include them. The entire util library is included, right? Not really just the required library class. So static linking, dynamic linking. Okay. So, and they are linked together. For example, system libraries and the program code are combined together into the same binary code image. So that is static binding. So which one is more efficient? Dynamic linking or static linking? Obviously dynamic linking, right? So, you don't really require it. You don't even need to, until the execution time, you don't need to link it. So that's better. So smallest piece of code is called stub. A stub, right? Memory resident library routine is a stub. So each routine is a stub. So just a terminology, nothing more. stub is replacing itself with the address of the routine. So, so you're still getting them. Dynamic linking is particularly useful for libraries, especially, right? I will show you the system with the libraries, the loading. An example. I will give you an example. We have an example with the DLL. Okay, swapping. Swapping is temporarily keeping the program out of the memory. Okay, so in the virtual memory, right? Virtual memory, and your disk memory or virtual memory, and then bring it back and forth, right? So whenever you require it, you bring it to the main memory, or otherwise put it on the disk actually again, right? So disk, if it is a faster disk, it's easier for you to have this backing store. So roll in, roll out, right? Swap in, swap out, or so low priority process normally are swapped out, because if you want to really execute it again and again, so you would not really be efficient. So operating system has to make a decision which one should be swapped. If swapping is allowed, swapping doesn't need to be allowed. You can disable swapping in the operating system, but desktop operating system, people has leave it, swapping. That's why, whenever a program is taking so much of time, so, there are a lot of processes are running at the same time. So you worthwhile actually, rebooting your PC, because sometimes, so you are running so many processes in the background, it's not worth it. So it'll be swapping. So if it is swapping, it takes a lot of time. Okay. So basically, should you keep it exactly the same place? It depends on the binding method, right? Okay. So IO requests and the memory allocation. Okay, you completely put it back to the memory. You know what? What is the idea of actually swapping out? Because you want to reusing the space to some other program. So when you require to reload again, you may not get that exact location. So you need to actually rearrange again the process. Okay. Swapping normally is disabled in some of the operating systems, right? So again, these days, swapping means is a big problem, because the enough memory is available these days for running programs. So that means swapping can be disabled to safeguard your, the performance of the machine. Okay, swapping out, swapping in. So it's going to the disk, process is going to the disk, process is coming back to the disk, to the main memory. So swapping in, that's a view of this. Context switching is not swapping. Okay. So sometimes, right, context switching, including the swapping. So that's the additional burden, right, isn't it? So first of all, you need to bring it to the main memory and then put it into the context. Context means putting it to the execution space of the CPU. So there are other putting things into registers, open files, and so many things like that, right, isn't it? So what is the most important thing in the context switching? So making sure that process control block, right, PCB, is respected. PCB, right? What is it? PCB? Process control block. The set of variables that define the current state of the program, state of a process. What are the open files? What are the registered contents? Which instruction currently being executed? PC value. So, and all the base register and everything that you need to know about the process uniquely to identify each instruction is in the PCB. So using that information, you will be able to precisely pinpoint where to execute. Swapping in, swapping out. So it takes 2 seconds is a lot of time. Okay. So for a computer, right? But even that 2 seconds is okay for a human point of view, but it multiplies when you actually swap, multiple. Once it's like start swapping, it's like a chain reaction. So that means when you run out of memory, It's like run out of cash in your pocket. So it's going to last some time, a profound effect on you, so that you don't have money, because any money comes in, immediately you spend. So that means you become again poor. So poor people suffer a lot. So that's the same thing here too. So when you are running out of the main memory, you are like a poor person. And then, any memory which is really right away used, and you become poor again. So, memory can be requested, like a memory request, memory release. Can you give me an example? Memory management unit, right, can allow you to actually, requesting the memory. So there are two types of requests. One is internal, another is external. External means user process can request memory. So that is the memory request. You can actually, do dynamic memory, which is heap memory. You can request. So like a malloc or any system call can request for memory. But for the process to load into the paging, so you have a memory request, memory release. So you're taking out the memory out of the pages. Okay. So sometimes, right, your virtual memory is full up already. So you can't even swap out. So then you have a big problem, right? Okay. So you would like to avoid, so transferring the IO to the kernel space and then to the device, like a two-way buffering, like, you're giving it to the kernel to do the work for you. So you don't want to really waste your, kernel space. So sometimes you can't swap out right away. Somebody got to safeguard that, which is kernel. And it will use its own memory to do that, right? Standard swapping is not used in modern operating systems. So swapping, like I told you already. So operating systems, because it's very low, very, so free memory is extremely low only when you have a problem. Also, again, it takes much more time actually to swap out, right? So it's that's why swapping is not recommended. Okay, so it's not supported mainly, right? So in some of the platforms, especially iOS, Android, okay, you can actually configure whether you want to swapping or not swapping, and its default is no swapping pages, right? Okay, main memory. So algorithms you want to really see, and allocation algorithms, contiguous allocation, non-contiguous allocation. Okay, so main memory is basically a limited resource. Okay, and you have to allocate very efficiently without wasting any of the memory, right? So contiguous memory allocation was one of the early methods. But now sophisticated methods are being used, and even scheduling is sophisticated, right? So main memory used two partitions. So operating system, okay. So and I got user processes, right? So each process is contain a single contiguous section of memory. Okay. So single contiguous memory. So everything is one place. Relocation register. So to protect the user processes from each other. When you're changing the operating system code and the data. Base register is containing the smallest physical address, right, of the process. So limit register contains the range of the logical addresses, and MMU is actually logically deriving the address. And it is making sure that the same thing that we have talked about earlier here. Look at that. So you take the logical address, should be within the limit. Okay, then only you take it, and then add it to the relocation register. Okay, and then create the physical address. Okay, if this is not the case, create a trap. Trap is an exception. Okay. So multiple partition allocation. So that means, the contiguous memory allocation, non-contiguous allocation, right? Degree of multi-programming, multiple programming, multiple partitions are being used. So the number of partitions you have is the degree of multi-programming, right? The number of each partition is allocated, okay, to only one process, right? And a variable partition size. So then, we talked about if a process is completed execution, that piece of memory is becoming a whole. And the size of the whole should be big enough to accommodate a new process if you want to allocate. The same story actually I talked about already. So process is exiting, becomes a free partition and becomes, two partitions are actually freed up. So they're combined together to become a single whole. Okay. So 2 or 3 partitions, adjacent partitions are combined together to make a single whole. So operating system is maintaining the allocated partitions and also holes. And we were talking about here, look at this here. The process completed execution. So it became a whole. And another process came in and allocated. So which means that, whole becomes smaller whole. So another process came in again. So it's able to accommodate, the whole is able to accommodate. So whole became smaller. So this is still efficient than, fixed size, partitions, or you cannot, change the partition size once it is made at the beginning. Variable size partition, is going to be efficient compared to the fixed partition, right? And fixed partition has 2 cases. One is equal size, another is unequal size. And there are, first fit, best fit, and the worst fit. I also taught you another method called next fit, right? Isn't it? So next fit, you didn't write it here. Next fit means it's starting from the place where it's allocated the memory and going forward. The first fit is always looking for the smallest hole which is available. Best fit, sorry. The first fit is always finding the first hole that is big enough to accommodate. The best fit is the smallest all the time. Worst fit is the largest hole. Okay. So again, you would like to want to minimize external fragmentation and internal fragmentation. So the total amount of memory which is unused within, within one partition is internal fragmentation. External fragmentation is total amount of memory space wasted. Okay, because of non-contiguous. So you will not be able to use it. Give me an example, sir. For example, we have 2 holes. One hole is, 50 megabyte. Another hole is like, 70 megabyte. But another process came in for, 100 megabyte. You will not be able to load it because none of these partitions are able to fit that. First fit algorithm. Okay, you have n blocks allocated. So there is a 0.5 chances that you are actually losing, memory space. So roughly, it's not really accurate. 1/3 of the, maybe unusable. 1/3 is unusable. This is called 50% rule. Okay, 50% rule. All right. So why 1/3 is like a 50% rule, right? Why not 35% rule or something like that? So anyway, 35, 30, 30 becomes 60. So if you, usually most of the time, so it is, there could be a process which will be taking, only 2 bytes and the entire partition is wasted, right? So that's why 1/3 is a rule of thumb, nothing special or something. So reduce external fragmentation by compaction. So that means that several holes are there. So then you can put them together, okay, by rearranging shuffling the memory contents. to the free and put them together and then try to actually make a bigger whole. That's called compaction. So compaction is a big process of actually moving the memory, shuffling around. It takes a huge amount of time. So you don't really do compaction even on the disk. It takes, disk compaction. So if you're talking about a memory compaction, so they're moving the process around, right? So, and the disk compaction is moving the programs around. Segmentation. So allocate, each piece of logical unit to a particular, segment, which is the main program, or if you have procedures, for example, or functions, or methods, or even objects, they can be allocated in a particular piece of memory. Okay. So, and then managing all of it, right, is a lot of work. So that means every, unit, a logical unit, is loaded into one or more segments. And then you have to identify the segment and then actually get the instruction from there, or a data from there, or a variable. Okay, from there. What is the difference between data and variables, sir? Variables can be allocated on the stack. So data is allocated usually either on the heap or static memory, right? We say static memory in Java, but in other programming languages, you can say data. BSS, block, protected, segmented, memory. So, common block, stack, symbol table, arrays. These are all the logical views of, the program. A program. See, look at stack table or stack memory. Okay. And this is a function. A function. Library function, to really say. This is a main program, your program. These subroutines could be, dynamically linked, or you don't even need, some time. So symbol table. Once you resolve all the symbols, right, into addresses, you don't need a symbol table. Or you want to keep them like a piece of memory in the system, then it's okay. So logical view of segmentation, segment 1, 2, 3. So they're non-contiguous. Look at them. Don't need to be contiguous. So 1, 4, 2, 3, they can be loaded even anywhere in the physical memory, right? So logical address is consisting of two tuples. Like, you have a, segment number and offset within the segment. Logical address. You see, we were talking about, isn't it? You take, for example, 8-bit address or 4-bit address. Okay, you have 8 bits. So segment number is the high order bits. And the offset within that is low order bits. So the way in which you organize, so the number of segments you can say. For example, you take 3 bits, for the segment number, you get 8 segments, 0 to 7. And that will be high end, number of bits. So it'll be still in the address space, logical address space, or physical address space, whichever, right? So you will be able to translate. You have to map, okay, into the right physical address. So base register is containing the physical address. The segment is on the limit register is specifying the length of the segment. Okay, segment table base register, segment table length register. Okay, so the segment number should be legal enough. Otherwise, you have a wrong address, right? You create a trap. Protection. Memory protection is fundamental for the operating system. Okay, so there's a bit dedicated for validation bit. So if there is any legal segment, or legal segment is okay segment, right? So you can actually dedicate a bit. I will show you an example. Without an example, you probably won't appreciate. So Production bits. You know, operating system, teaching operating system, I was teaching Unix operating system in the past, you know, like 10 years ago. So understanding the bit level, you know, data structures is fundamental in operating system. I'm not teaching to that level at this point. I was teaching a graduate course at the time. So we were looking at the bits and pieces of each you know, data structure in the operating systems, especially Unix. That book was like a Bible, a very, very good book. So here, look at that. So segment table. So you have a CPU, you have a segment number, and the displacement and offset right here. So segment number again is actually, you know, validated, right? You know, segment, you have a limit, and then the base segment table. It should be within the segment is valid, right? Okay. And with the displacement is within that. So which means that you replace the segment number. Okay. That means you actually are taking the physical address to go and translate the address validity, right? Address validity within the segment table. You're taking the segment and then putting it in there. So and then validating it. Okay. Physical address space is non-contiguous allocation, right? Are non-contiguous. Pages are not contiguous. So dividing the memory called frames. Remember we were saying earlier the physical memory frame, logical memory is page. So in the context of the program, we use pages. In the context of you know, RAM, we are saying frames, and both are exactly the same size. Okay, and the power size is power of 2. Okay, so 512 means what? 10 to the power of 2 to the power of 9 is 512, right? So 16 megabytes. 16 megabytes to 16 means 2 to the power of 4. Mega means 2 to the power of 20, right? Isn't it? 2 to the power of 24 is 16 megabytes. Kilo multiplied by kilo is mega, right? Okay, so a program may have n pages. That means you are putting into n frames. So you have to look for n free frames to load them. And a page table is going to translate the logical address to physical address. So that means you have logical address, which is a page number here, and the offset here, and you replace the page number with the you know, the frame number, right? So you'll still have internal fragmentation because the last page or frame of the process is not 100%. Let me actually put in a mute, right? Let me go to the participants. I think again, Suraya.
Oh, sorry.
I'll put you on mute. I have to put you on mute, right? Don't unmute yourself, Suraya. Just leave it on the mute. Okay, all right. So address translation scheme, like I told you earlier, right? Page number is there and you change it to frame number, and that's it. So you get the physical address. So, but you're coming from the page table to get that translation. Okay. So what you have here is M is the total number of bits is M. Okay, offset bits is N. Is basically displacement. Okay. So value of the displacement. Offset is a number, right, for you? Well, within the page, and it will be within the frame. So that means the number of bits that you're using out of the M, you know, P, like a P, right? P is the page number. So, but How many bits you require for the page number? M minus n. Okay, M is the total number of bits for the address, logical address or physical address. This is logical address. Logical address. So that means you actually, when you translate that to physical address, is like RAM address. The number of bits will be more anyway, so right, isn't it? Because the page numbers are not the same, the frame number. See, the frames are kept in the page table. Okay, so the page number is taken and replaced with the frame number. Then it becomes a physical address. The displacement is still the same displacement. Offset is still the same offset. So that translation will let you find the physical address space or physical instruction. So this is an example. Okay, frame number, page number. So page 0 is what is the frame number? 1, right? So page 1 is frame number 4. So what you keep in the frame is page table is the frame number. You understand me? So how many page frames you have in the physical memory in this example? Hello?
8 frames.
8. So 8 means how many bits do you require to represent 8?
3 bits.
3 bits. And you have how many pages you have in your page table?
4.
4. So how many bits you require for the page number?
2.
2 bits. So which means that, here, so 2 bits. And offset, we don't know. You didn't tell me anything about the size of the each frame or a page. So we can't talk about it. But so your physical address, logical address, you're allocating 2 bits. And you got to translate that. This is the offset. Offset is displacement, right? And when you translate that, you take this 2 bits and you actually put the 3 bits. So you're allocating a bigger space here. Okay, the frame number or frame, the physical address is bigger than the logical address. Always, at least equal. Okay, at the equal, greater than or equal. So he's giving you now some example, concrete example. So memory is 32 bytes. So 2 to the power of 5. Do you agree with me? 2 to the power of 5. And the number of pages, like 4 byte pages. 4 byte page means how many bits, how many bytes can you put in? 4 bytes, obviously, right? 2 to the power of 2. How many bits you require for offset?
8.
Come on, sir. Offset, 2 bits. So you see, 4 byte. Each page is how many? What is the size of each page? How many bytes is it? Come on, guys. So 4 bytes written down here. Each page is 4 bytes. So what is the frame size?
The same.
Same, 4 bytes. So that means the displacement requires only 2 bits. If you take the address, the displacement, the n is only 2 bits. That's the n. The entire space m, right? We were saying m is the number of bits of an address. Okay. So now here you require 5 bits to represent, physical memory here, right? Isn't it? But the logical memory, look at it. How many pages you have? Oh, I see. Here is, yeah. The entire process here is only 16 byte process. What is the size of the process? 16 bytes. Do you agree with me? 2 to the power of 4, is it not? Is 16. Do you agree? So what is the page number? How many pages?
4.
Yeah, 4 pages. How many page number bits? How many bits are per page number? 2
4.
bits. Come on, why 4, sir? Because this is 2 to the power of 4 is for the entire process. It is segmented into pages. So that means 4 bits are required for logical address. 4 bits, I agree with you, 4 bits. If you say that that's a logical address, but it's not page number bits. Offset is 2 bits and the page number is 2 bits. So 2 bits. And this one is 3 bits. You understand me? Hello?
Yes.
Yeah. So you take the page number, go to page table and take the frame number, put it into the this location. This is physical address. This is logical address. Logical requires 4 bits. The physical requires 5 bits. Okay? You clearly understood, right? Isn't it? Hello? So look at it. This is page number 0, page number 1, page number 2, page number 3. So page number 0 is loaded into frame number 5. Frame number 5. You didn't put the 5 here, right? Oh, yeah. You didn't put the page number 0
It's at 20.
at the
Page
20. Yeah.
5.
Yeah, you're right. Yeah. I was reading, I was looking at that. I'm making a mistake. It's a frame. That's why I actually, this one, I added this. The frame number 5, frame number 6, and so because the textbook did not give. So, and it gives you very clear picture. Look at that. Okay. So A, B, C, D are the bytes loaded there. And again, the second one is page number 6, E, F, G, H. And the third one is like page number 1. Frame number 1, sorry, frame number 1. And the next one is that. So you can clearly see the allocation of memory, okay, into the segmented, right? Good example, a simple example. I took, I think, 64-bit byte allocation, but you can see here. So page size is, for example, another example here. Okay, page size is 2 kilobytes. How many bytes? 2 kilobytes. 2048, right? 2 kilobytes. 2 kilobytes is how many? What is the 2 to the power of? Come on, guys.
10.
2 to the power of 10 is kilobyte.
20.
But 2 kilobyte. 2 KB. So 2 multiplied by 2 to the power of 10 is 2 to the power of 11. No? Yes or no?
Yeah.
Yeah. So page size, each page is this much, these many bytes. So how many pages? The process size is this one. How many pages do you require? So this one divide by that. Okay. And you take a reminder plus 1. If reminder is 0 plus 1, exactly the number, but if reminder is not 0, then plus 1. You understand me? The last page, okay, 35 full pages plus 1086 bytes. You agree with me? Which will be one more page. Okay. Do you agree with me? Yes or no? So 72,766 divided by 2048 is equal to 35. And the remainder is 1086. Do you agree with me? Hello? You should do it. So this is the questions I can ask. There is nothing else I can ask. How many pages do you require? How many, that should be the question. If I go here. Okay. Good. Equal to 72,766 divided by 2048. So it's 35. 35.53. Okay. So how many bytes are remaining? This one minus 35 equal to this one multiplied by, okay, and what did we divide with actually? 2048. So 1086. So 1086 bytes were supposed to be allocated into a different page. So it's segmented into another page. So which is like, you have 36 pages. So the last page is internal fragmentation. So 2048 minus 1086 is 962 bytes are wasted. Okay. Worst case segmentation can be, you know, 1 byte requires the entire space, isn't it? Do you agree with me? What is the worst case fragmentation, internal fragmentation? 2047. Do you agree with me? Hello?
Yeah.
Is equal to 2047 bytes. Okay. On average, you're
How did
losing.
you get 1086 bytes after you divided by
You know, basically what you did is you have the reminder, right? Reminder.
which was 0.53?
And that's what you multiply with 2048 because that's
Okay, you
divided.
multiply that by 2048 again. Okay.
Yeah.
Okay, thanks.
Yeah. But don't round anything though, because if you round anything, you do not get exactly the same. You do the real division if you want. I think it will give you modulo if you want modulo. Let me see. Modulo will give you a reminder directly in Excel. Modulo is not there, I think I have modulo. No? Mod is, yeah, let's say mod. Yeah, number and the divisor. See, you will get that. So 72, 766, comma, 2048. You'll get the reminder directly. Yeah? Do you agree with me? See it, no?
Yeah.
So in Excel, there's a modulo function which gives you reminder. In your, Java programming, what do you do actually? 72, 766. Yeah, percentage sign, right? Isn't it?
Yeah.
2048. And you get your thing, but here you don't, because you have to use the modulo function in Excel, mod function. It'll give you directly. You don't need to multiply and all. Okay. So worst case scenario, like fragmentation is the entire frame, just for 1 byte, you allocate the entire frame, which means that 2047 bytes can be potentially lost. Okay. But that doesn't happen all the time. So, on average, half of the frame is wasted. That makes much more sense because sometimes less than half, sometimes more than half. On average, it's half because it's random. You don't know, and uniformly distributed. So that's why it's half. So small frames sizes are desirable. Yeah, it is true. But the issue is, managing them itself will be actually, bigger issue, right? Isn't it? If you have smaller size frames, then your page table is becoming bigger. So you are going to actually spend more efforts into the maintaining the page table. So you don't want too much page table too. Okay. So page table size is growing over the time, Solaris is supporting, 4 kilobyte, 8 kilobyte, pages and 4 megabyte pages, right? Now 2 page sizes. So 8 kilobyte. So the processes which are big enough, so allocate 8 megabyte, and the processes which are small, they allocate 8 kilobyte. Even in the buffers in the telecommunication, right? I was using, different size buffers, 16 byte buffers, 128 buffers, and 1 kilobyte buffers to write memory. So it's a way that you write the operating system. Process view and process view is logical view, and physical memory is a totally different because you are looking at the RAM. This is with the logical, basically, zero relative. Okay. So implementation of process can access its own memory. That's the whole idea, right? Isn't it? Before you allocate, okay, everything is contiguous and relative, right? Isn't it? So let's see, look at page 0, page 1, page 2, page 3. So that's, physical memory. Okay. And you allocate them. Before you allocate, this is a RAM, okay? That's the RAM. After you allocate, you have taken this one. This is a page table. Do you agree with me? So if you want to load, you have to allocate them to pages, frames. Which frame was allocated? Page number 0, 14. Okay. So all this is freely available. Okay. And one is allocated in frame number 13 and 18 and 20. It's okay, no? It's okay. So this is a before and after allocation of a process, which is exactly the same size. So don't forget that the page table itself must be loaded into one of the pages. It's not shown here, right? Isn't it? Hello? In this figure, where is the page table? Do you have it? Yes or no? It is still in the,
It
yeah,
doesn't show it.
it doesn't show, but it should be allocated within one of the pages. Frames. So you shouldn't forget that. So even that, what is the size of the page table? What is the size of the page table? The last frame here, what is the size? Which one is the last frame? 21, right? Okay. So how many bits do you require for frame number? How many bits?
We need 5.
Yeah, you need 5 bits for frame number alone. You understand, right? And we don't know the size of, size of the page size. So I can't tell you the physical address bits. I can't tell what the M is. If I know the page size or frame size, I will be able to tell you the physical address, the number of bits in the physical address and the logical address also. Okay, page number should be allocated. So, page table is kept in the memory. So that's in this coming and telling you right now. Page table is kept in the memory. So page table base register is pointing to the page table, right? Okay. Page table length register, it is telling the size of the page table. So you're validating again for for loading purpose, right? So data and instruction access are 2 memory accesses, right? So instruction access. So that means you got to allocate, look at the page table first and then go to the instruction and get it. So page table access is one access. And then going to the actual memory is another access, which means that if you go here, suppose this is the page table. So looking at the page table is the first thing you do. And then you go to the write address. So address translation, look aside buffers. What happens is, okay, what happens is there are two accesses. One access is here for the lookup. And another access is the actual instruction. But both are in the main memory. But the problem with the main memory is what? It is slow. Do you agree with me? Memory access, what is the sequence of faster memory? Faster memory is register, right? Fastest memory is what? Which one is the fastest memory?
Register.
Register. What is the next memory?
Cache.
Cache memory. And the next one is the main memory. So which means that this memory access here, accessing this page, once you get the value, don't put it there. Put it in the cache. Okay? Cache memory. Cache memory is a limited memory. And you create a, another table called, memory translation look aside. You see, I have a figure for that somewhere. So look at that. So I'll come back to that. This is the, translation look aside buffer. I will come back to that. So that's the cache memory. So which means that you don't need, first of all, look at the cache memory and then only access the main memory. So that's called, okay, translation look aside buffer. So for address identification. Okay. So which means that each time you did find the right translation, and it is frequently used page, because the code, right? When you're executing the code, your code may not be running all the time the same way, So sometimes your program may not be accessing, certain routines. Then keeping that into the, look aside buffer, it's not worthwhile. So when you actually, access a page table for that instruction, then you actually put it in you already searched for the translation. So why don't you keep that information so that you don't need to look for the translation again? Okay, that's the purpose of this, translation look aside buffer. Okay, and you keep it a small table. Okay, 64 to 1024 entries. So that means 1024. After that 1024 is finished, you don't keep that anymore in the translation look aside unless you free it. Okay, so that you can maintain on 1 bit, or a few bits to see how long was recently allocated. How many times you looked at it or something. So associative memory. So associating the page number to frame number. Like searching the page number and then finding the frame number, right? Okay. All right, sir. So look at the page number and frame number are kept. In real page table, you don't keep the page number. This is a page table. Do you keep the page table here? A page number here in the page table? Hello?
No.
No. Then how do you find the page table? Frame number, index. You take this one. Okay. That is the index. This is an array, right? Is it not array? In your Java, did you study arrays?
Yes.
So array. So, but basically what you have is page table is array of frame numbers. So whatever is like an integer, right? Frame number is an integer. So it's an integer array. It's an integer array. So that means you are taking the index and going to the right element and taking the element value is the page number, frame number, and replace it in the physical address space. And that's it. So, but each time you look at the page table, you write down inside what? TLB. So first you look at the TLB. If it is hit, you found it already, you found it faster. It is faster than looking at a page table, significantly faster. So that means, so that's why you don't want to really, accessing the page table every time. Okay. Do you agree with me? Yes or no? The hit ratio is alpha. What is the meaning of hit ratio? Percentage of times you found the page table, page number in the TLB. You understand me, right? You understand the hit ratio? What the meaning of it? The number of times you are able to find in the frequency of the frequency of finding. Okay. There is 80% chance that you will find the page number in the TLB. Then it is alpha is 80, right? Isn't it? or 0.8. Okay, and it takes 10 nanoseconds to access the memory. How much time it access to access the memory? 10 nanoseconds. 10 nanoseconds. Okay, and 10, which I think is not written very well for the TLB search though. Okay, we spend 10 nanoseconds. Like 80% chance of finding in the TLB means what is the chance of not finding in the TLB? 20%. Do you agree with me?
Yes.
Yeah, and to search the main memory, it takes twice as much time. So that means how many nanoseconds will take? 20 nanoseconds, right? So 10% of the time you are spending 20 nanoseconds. 80% of the time you are spending 10 nanoseconds. On average, your access time for each access is 12 nanoseconds. So there is a 20% slowdown of your memory access. Of course, you cannot really make it 100%. If it is 100% means what? All entries are in the TLB, then it's 100% chance of finding it in the TLB. Okay, TLB is cache memory. That's why it's 10 nanoseconds. Regular memory is, main memory, right? RAM memory. It's 20 nanoseconds. Okay, all right. And if it is consider more realistic hit ratios, 99% you're getting it into the cache memory. So 99 multiplied by 10 and 0.01, like in 1% chance of finding it into spending 20 million. So that means 10.1 nanoseconds. It's only just 1% slowdown, right? Okay, just 1%. You don't need to compute, say it. This slowdown is this one. It's 1% slowdown. That's resulting to 10.1 nanosecond instead of 10. 10, it is 100%. You find it in the TLB. Okay, so you know what? There is a bit for we want to understand memory, what type of access you are getting. There's a protection bit. Okay, whether it's assigned or not assigned kind of bit, right? And a valid bit. Valid bit is to make sure that so page table is a size. Is it really allocated? Not allocated? You want to understand. Sometimes, right, page table may be bigger than your real need for it. Okay, you have a page table length register, page table base register. We were talking about them, right? Maybe we should take a break and then look at this example. Looks very good example. It's very straightforward example also because you've done so many of them like that. Okay, so here he is actually telling you what is the size of the process. Come on, guys. This is the one which is given to you. 12,288 bytes. So each page is, our frame is 2 kilobyte. So you need 6 pages. The number of pages you require is 6 pages. Is it exactly divisible or no? Can anyone do it, please? 12,288 divided by 2048. Is it exactly 6 or 5 and something?
It's exactly 6.
Exactly 6. Okay, the exactly 6 is no wastage, no internal fragmentation. So you understand that this is given. This is given. You understand that you derived it. Okay, that's why I'm showing you the red font here is given and the black font is not given. You're computing. The black font is you're computing it. So 2 pages will be marked invalid. So how many pages do you require? So, if you want to specify here 6 pages, right? To represent 6 pages, how many bits are in the page table? How many bits to represent page table? Page number bits. How many bits you require per page number?
3 bits.
You have 0 to 7 pages, right? Do you agree with me? Is it not 3 bits? I even wrote down here. You have 0 to 7, right? The page number. But how many bits are actually pages are really used? Only 6. How many pages are not really used? 2 pages are not really used in a page table. So the V bit, you understand me? The valid bit, invalid bit, what is the purpose of it? Is it filled or not filled? You understand me? Technically speaking, you will never go there. You will never access. You're not supposed to access the page numbers which are invalid in the invalid means those and there's no entry. The entry for frame number is not valid. So this frame number here is 00. They're not valid. Not valid. Do you agree with me? You may be asking me a question. Why do you allocate in the first place more than 6, sir? You allocate only 6. So page table size can be 6 multiplied by whatever is the frame number size is, right? Isn't it? 6 or 7? Say yeah, 6. It can be 6 multiplied by whatever is the frame number bits. Okay, but in reality, you use usually the page table in the 2 to the power of some number, like 2 to the power of 3, 2 to the power of 4, 2 to the power of 5, like that. Then you will not, your page table is not exactly. Okay, so fitting, exactly fitting. That means, so there are pages which are left over, or page numbers which are left over, which are frame numbers which are 00, which are invalid. So you can say invalid bit. A bit will tell you whether this frame number is valid bit frame number or invalid frame number. Don't see any other case of invalid frame numbers except this. Okay, so the logical address space that you require to this process, right? Isn't it? Okay, so logical address space is 14-bit addresses. It gave you here 14-bit address. What is it giving you? 14-bit address. 14-bit address is given to you. The 14 bits you require. 2 to the power of 14. These are the size of the process here, isn't it? Okay. But really speaking, I think this is one example. There is another example, either 2 examples. I think I should have been very clear to you. So, this page has 2 schemes here, like 8 pages. This is also 8 pages. Look at that. So 2 kilobyte is 2 to the power of 11, right? Isn't it? So the total space divided by the page size equal to 8 pages you have. So 0 to 7. That's fine. So it's completely loaded. No problem. But the process here, you have only 6 pages. Okay. It is this scheme here is fully loaded. So there is no invalid frames in this case, right? Is it not? All are valid frames. You agree with me? And here, in this example, okay, you have some pages which are not used. In the first example, okay, is fully used. I think I should be more clear, no? Because you don't, unless I explain, you don't really understand. Example 1, fully loaded. The process is fully using the page table. The process is not fully using the page table. Okay, both are different examples. Yes or no? No? This example, right, which I gave you, this one will not have any invalid pages. Do you agree with me? The first example, do you have invalid pages? The page table of this scheme will never have I bit, right? Isn't it? All will be V bits. Because the size of the page, the address, is full, is the logical address space is this one, and the size of the process is that. Okay. Or Okay, this is the scheme for 14-bit addresses. But you require 14-bit address for this one also. Do you agree with me? Hello?
Yes.
So 14-bit addresses for this also, you use the 14-bit address, then you have invalid bits, frames, and so on. Okay. Okay, let us see here. Because you're using the same page table, page table, you're using the same page table means that addressing scheme is the same. You require 3 bits here too. Whether you use it or you don't use it, you still require 3 bits. Which means that, you see, for example, 6. What is 6? 6 is 0. Okay. 6 is 0 or 110, right? 110. Okay. 110. 6 is 110. Okay. You have 6 pages, right? 0 to 6 pages. Yeah, 6 pages. So 6 pages means there's only 1 page is wasted, right? Why did I put? Yeah, 0 to 6 pages means 0 to 5, right? Isn't it? Page is 0 relative. 0 to 5 pages is 6 pages. The page number is 0 to 5 page number. 0 to 5 page number means 6 pages. Okay. So that means there is this like, the page number bits are like, so 0, 0, 0, and 7 is 111, right? Isn't it? So 111 and 110. Okay, 100. So like that, right? 101, sorry. This 5 is 101. 6 is 110. 7 is 10. So the 3 bits are actually required for you because you have 101. You cannot go to 101 without even 4. You cannot go. 100 is 4. So they look at that here. So you require these bits must be set. All other bits, that most significant bit is not set. So the logical address is defining there. So we want to take a break now or no? We did substantially good progress because I think we have done that other thing in detail, right? Good progress. And the remaining thing I think they will finish, so after the break. And once I finish this chapter, okay, and then I stop for the day, okay?
Okay.
So let's take a break now. How much time? 10:30? 20 minutes or even more? It's up to you. You tell me is granted. We all have a break, so it's not just you, me too, right? So
10:30 is good.
yeah, 10:30. We come back at 10:30 and then finish maybe, as soon as we can. Hello, 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 hello. Hello, hello, hello.
Hello.
So thank
Hi.
you, Adriana. So coming back again, I hope everyone is here. So let's continue
Yes, sir.
what we need to do and then actually finish it off maybe by 11 or something. I hope. I'm not sure that we'll be able to finish in 11, but looks like. So look at it now. So do you see my screen? Not yet, right? I'm not sharing the screen yet. Okay, all right. I'm going to share my screen, okay? So it's a lot easier to understand this topic here than my other thing. I gave so many examples in other place here. Here I'm just giving few examples from the textbook. So logical address space. So when you require 3 bits, the maximum addressable space that you will have follows. Where is my pencil here? Here. The logical address space. This is the maximum amount of addressing you can accomplish. Okay. But the processing may not be that much. process may be, this is a concrete example. Maybe, process is only just 12,288 bytes. In such case, you don't require 8 pages. Okay. You only have 6 pages, which are 0 to 5. Okay. That means some of the pages are invalid. In this case, only the case where the number of bits is not fully used in the address space. So that's where the issue comes in. I won't say number of bits. Bits are used, but there are pages which are not really used here in the page table. Okay. All right. So that means, you will have the space which is less than what is maximum possible. Okay. This is a shared code. Okay. Okay. All right. For example, there are pages which are shared among so many processes. You understand me, right? Okay. So only one copy is required, not all, every, you can, several processes are sharing the same code, for example, like libraries. So like a Java library, util, scanner, random. So many libraries are used by several processes. You don't want to load them several times. Okay. You can just load once and then actually we use it again. Okay. And something which is private code. Private code means no one will be able to access that code. This one, multiple pages can be accessing the code. Anyway, code is code, it's not data. Data must be private anyway. Your data cannot be used by somebody else unless you give access to somebody else via giving the reference, right? How do you give the access to somebody else? Can anyone tell me, please? I already answered you. So I'm asking you to tell me what I said a few minutes ago. How do you give access to your process memory? Especially data. Code is anyway read only. You cannot really write. You understand me? The only way to write into the code is patching. Like you can directly go there and put it in the address space, that overriding the operating system protection. Operating system in a normal environment, you will not be able to write anything in the code. Did you write anything in the code, sir? I did several times because I directly go to the memory and then patch it. But you don't do it, regular users don't do it. Even the regular programmers don't do it. Even myself, right? I was doing it because they're compiling everything. It takes a lot of time. And when I'm doing, I have to be very, very careful. A simple mistake is going to crash the program. So that's why, but again, you can always reload it, right? So, okay. So the process is keeping a separate copy of the code and the data, which is private. Okay. And you are keeping them in the pages, right? Again, pages for the code, pages for the data. They're not combined together. Doesn't make any sense to combine them together. Okay. Like a static data, for example, is one of the pages. You allocate them. And then, and that's the data. Allocate some memory. It doesn't need to be paged memory. Somewhere else also you can allocate. Okay. Anyway, so let us look at the shared code here is a common library 1, 2, 3, 4 libraries, right? Do you agree with me? Libraries here. And these are shared by everyone else. So these are also loaded into the memory like a page table, right? Isn't it process 1 page table? Oh, I see. So it's not the library. Process 1 is using library 1, 2, 3, 4. Okay. And the code of the process 1. Process 3, process 2. They're all using the same library. Some may be using they're all using the same library. But the library is available already in some pages. Do you agree with me? So that means page table is keeping the track of them. So when you try to use it, okay, the physical memory is not reloading everything, but your logical page table, the page table is including the libraries. Page table, look at that. Library 1 in page 3 library 2 is frame for not page, right? Page set frame. Why are you not really telling me, correcting me when I make a mistake? So this is the frame number. So page table contains the frame number, right? Page table contains what? Frame numbers. So the same frame numbers are shared. Is it clear or no? Standard library C library. Is it clear? Yes, no?
Yes.
Yeah. And giving your own, I think I asked you a question, but I did not get the answer and I did not follow it up. So, how do you give access to your own data to some other process? By giving reference to them or address to them. That's it. If you know the address, if I have the key of your home, I can open the home. Okay. The logical, consider a 32-bit logical address space. 32-bit logical address space means what? 4 GB of memory you can have, isn't it? The total memory is 4 GB. We said that earlier. 2 to the power of 32. Okay. Which is 2 to the power of 2 multiplied by 2 to the power of 30. Equal to the power of 2 is 4. 2 to the power of 30 is gigabyte. Okay. So the page size is 2 kilobyte. 2 to the power of 12. So 2 to the power of 32 divided by 2 to the power of number of pages, right? Okay. Which is 2 to the power of 20. 2 to the power of 20 is what? Mega. Mega means what? Million. Okay. Mega means what? Million. Giga means what? A billion. Okay. So each table entry is 4 bytes. You agree with me? 4 bytes means what? How many bits is 4 bytes?
2.
32.
Yeah, 32 bits. Oh, yeah. For each entry is, yeah, you're right, sir. Each page table, each entry is 2 bits, like, you see, like 4 bytes, right? 2 to the power of 2 bytes. That means 4 addresses you have, right? Isn't it? Okay. So which means that what is the entry? Entry is the frame number, right? Is it not? Entry is the frame number. Did I give you the physical address space? No. 2 to the power of 20 I gave you. 2 to the power of 20. You 4 bytes each. Let me just go back again and try to see it carefully. Okay, all right. How many, the page table size, how many entries you have in the page table? How many pages you have in your thing? You have pages 2 to the power of 20 pages, right? Okay, 2 to the power of 12 pages. So that means 1 million pages. So 1 million entries. Okay. Each entry is 4 bytes. Each entry is not really like 2 bits or something. It's 4 bytes. Like you said, 32 bits is correct. So each table entry means page table is this. The entry is this. The entry is what? Entry is the page number. And what is the size of that? The size of that is 32 bits. Why 32 bits? Is 4 bytes. So 4 bytes is the size of the entry. So 32 bits. 32 bits. Page number is 4 bytes. 4 bytes means 32 bits. So 32 bits multiplied by 2 to the power of 10 or 20. So 32 bits means 4 bytes. Multiplied by 2 to the power of 20. Okay. This is mega. So 4 megabyte. I won't say mega physical address space. So I shouldn't say megabyte, yeah, but 1 million multiplied by 4 bytes is 4 megabyte is the size of the page table, right? Is it not? Size of the page table alone. Do you agree with me? 4 megabyte is the size of the page table. Yes or no? Come on, guys. Somebody just confirm
Yeah.
that what I said is right. Okay. So that's the size of the page table is 4 megabyte because 4 bytes are required for each entry and mega is the number of entries, which is 1 million. So that means 4 million bytes you require. Okay. And what does that mean by page table entry frame number? So that means how many pages you have, frames you have. How many frames you have? Can you tell me how many frames you have in the system, in the RAM? How many frames you have? If I say 4 billion, will you agree? 4 billion frames. Okay. Do you agree with me? 4 billion means what? 4 multiplied by 10 to the power of 9. So let's say
The number of frames, it should be 1 kilo. It's 1024.
1024.
Because we
Number
have
No, but number of frames required for this process. For this process, required is 1024. But I'm asking the size of the RAM. The size of the RAM, how many frames you have in the RAM? In the RAM. What is the frame? What is the frame number? How many bits is frame number? How many bits is the frame number?
Is it 3 or 5?
Frame number. Frame number is page table entry. Page table entry is what? Is it not a frame number? You take the page table. And each entry, what is it? It's a frame number. What is the size of a frame number? The entry size is the frame number size, right? Do you agree with me? This is a page table. This is page 5. The frame 25. Agree?
we
Our
can
page.
also we can also find it from the RAM size. We have 4 giga, so it's 32 bits, the frame.
Frame number is 32 bits.
Yeah.
So frame number is 32 bits. The RAM is 32, like 2 to the power of 32 is 4 gigabytes, 4 giga. 4 multiplied by 10 to the power of 9. Okay, frames you have. And each frame could be bigger, right? Isn't it? Obviously, what is the size of a page? Did he tell you size of a page?
4 kilobyte.
Yeah. So that means, 4 kilobyte. Each frame is 4 kilobyte. So that multiplied by 4 kilobyte. Kilobyte is 10 to the power of. Kilobyte is 2 to the power. So 10 to the power of 9, right? I put 2 to the 10 to the power of 9. I'll translate that. 2 to the power of what? 10, right? Is it not?
Yes.
This one, can you tell me what is it? 2 to the power of 30, right? Isn't it? Hello? 1 billion is 2 to the power of what? 1 billion equals to 10 to the power of 9. Do you agree with me? 1 billion. 1 billion is giga. Do you agree with me? Take giga. But in 10 to the power of, you're writing down 10 to the power of 9. That is correct. Kilo is 3, mega is 6, and giga is 10 to the power of 9. But if you translate it to 2 to the power of, in the computer, it's a 2 to the power of 30, right? Isn't it? Hello? Kilo.
Yeah.
Kilo means 2 to the power of 10. Equal to 10 to the power of 3. Do you agree? It's not exactly equal to number wise. This is 1024. This is 1000. I'm not talking about number wise. I'm talking about our notation wise. So 1 megabyte, mega means 2 to the power of 20 is equal to 10 to the power of 6. So 1 giga equal to 2 to the power of 30 and equal to 10 to the power of 9. Okay. So how many entries you have? 4 giga. 4 multiplied by 2 to the power of 30. So equal to 16 to the power 16 multiplied 2 to the power of 40. You see, tera. So you have, 16 terabyte of memory you have in the RAM. You understand me? Yeah, agree or no?
But
If I ask,
the logical address just 32, so we can't
Yeah,
address the.
but I'm talking about physical address, not logical address. Physical address. Logical address is a process, right? Logical address is a process address. The physical address is the RAM address. You're translating the logical address into physical address. You agree with me? So the number of pages is, pardon, hello? So you have 32 bits here. Okay, 32 bits here. So how many bits is 1024? 10 bits, right? Do you agree with me?
Yes.
So 10 bits. 10 bits is here. And then 22 bits here. The offset is 22 bits. Do you agree with me? 22 bits is offset. 22 bits. Offset should be 32 bits here. 22 bits is not the offset because 1024 is the number of frames needed. Oh, number of frames needed. So it's not the pages needed. So offset is also always a page number. Look at the page size is giving you the offset, right? 12 bits are required for offset. Yes or no? The page size is what? 4 kilobyte, isn't it?
Yes. So the offset will
Frame
be-
size is what? 4 kilobyte. 4 kilobyte is 2 to the power of 12. That means 12 bits are required for offset.
Exactly.
Do you agree? Yes or no?
Yeah.
And if it is a 32-bit logical address space, so M is this one. M is this one. Okay. And the whole thing. And the M minus, this is the 12 bits. N is, I think, yeah, N is this one. M minus N is 22 bits, right? That is the page number, page number bits equal to M minus N, which is 22 bits, is a page number bits. You probably won't use all the 22 bits for your page number because the issue is how many frames are needed for you? How many entries do you have? 1024 entries.
Is it 22 or 20?
20, yeah, 20. You're right, sir. Because 32 minus 12, right? You're absolutely right. Okay, 20 bits. 20 bits you require. Okay, all right. So for each entry is 4 bytes.
Just another question.
Go ahead.
Is since the page size is 2 to the power of 12.
Page size, yes, one page size is 4 kilobyte, which is 2 to the power of 12. Yes.
Yeah, sorry, I forgot my question.
No, go ahead. I think you're trying
No,
to.
I forgot my question. Sorry.
Okay, no problem. Anybody has any question? Page number bits in the logical address is 20. Offset within 12 bits. Total is 32 bits.
Okay, yeah,
Okay.
my question again. Since 2 to the power of 12, does 12 always, or does the power of always equal the offset? Since it's, in this case, it's 12 pages and it's 2 to the power of 12, does it always calculate that way? Or it just so happened that this example was 12 and 12?
No. We gave you here page size, which is 4 kilobyte, right? Do you agree?
Yeah.
I gave you. So that means each page is 4 kilobyte. Starting from 0 within the page, 0, 1, 2, 3, 4, up to 4 kilobyte minus 1, right?
Yeah.
So because the 0 relative. So at the 2 to the power of 12 minus 1 is the last address within the page. So 0 to the number of addresses you have within a page is 0 to 2 to the power of 12 minus 1. So those are the number of addresses you have within a page. Okay. So there's 4 kilobyte. Okay. And the frame is the same thing. Frame or page, both are logical addresses are the same, because the frame and the page are the same. The offset is the same. If you think of a logical address within one page, it is basically logical within one page, which is 0 relative. Each frame is 0 relative. Each page is 0 relative. You understand me, right? When you add the page number, it becomes complete logical address. You have taken few bits here. You divided into 2 parts. One is the page number, another is the offset. But this one is always 0 to something, right? Is it not? And this one is also 0 to something. If you take only this. So 0 to something is the number of pages. And the offset is the number of bytes here within the page. You understand me? Hello? Within a page, this is the address. Because your instruction or a piece of memory is somewhere in the memory, right? Isn't it? Could be this one. Yeah. And you want to figure out what that is. You find out the page number or frame number. If it is in the process, it's a page number. If it is in the in the frame, in the memory, main memory, in the RAM, it is a frame number. Offset is offset. Offset is always the same bits. The same bits. That doesn't change. The offset bits don't change. So look at here, offset is this one. It is the same offset. What you change is the page number to frame number. If you change the page number, it becomes immediately the address in the RAM. You put the page number, it is the process. You take the process, and somewhere in the process, you have that byte. So that is identified by the page number. You understand me? Hello? This is the
Yeah.
process. Process is divided into pages. And the frame RAM is divided into frames. So the process, the frames pages are 0, 1, 2, 3, like that. Page number. Okay, if you use 3 bits, for example, for page number, this one is 0, 0, 0. This one is 0, 0, 1. This one is 0, 0, 0, 1, 0, like that. And within that, you take a byte, for example. This is another, 5 bits, for example. You write a 5 bits and then put together. That is a pinpoint location within the process. Okay.
Yeah.
So you can identify exactly where it is located, each byte in the process, in the RAM also. Okay. So each page table entry is 4 bytes. That means frame number is 32 bits. 2 to the power of 32. 2 to the power of 32 means how many frames are possible? 32 bits, right? 32 bits. I already put in here. So 32 bits. So how many frames are possible? 2 to the power of 32. Okay. So many frames are possible because you have 4 bytes of like 32 bits for the frame number alone, which is the number of frames you have is 2 to the power of 32. But how many frames do you require out of these 232 to the power of 32? So 2 to the power of 32 means what? 4 billion pages, frames. 4 billion frames you have. Out of the 4 billion frames, how many frames do you require? So 2 to the power, this one is 2 to the power of 32, right? And this one is 2 to the power of 12, right? Isn't it? 2 to the power of 32? No, 22. 2 to the power of 22. Do you agree with me, 22? Mega means what?
Yeah, mega is 20.
Yeah. Mega is 20. Okay, all right. Mega is 20. I did have 4 mega, I wrote down 32, right? Isn't it 4-bit megabyte physical address space? Is it correct? Yeah, we'll look at it. Okay, we'll have to look at it carefully. Okay, all right. So 2 to the power of 32, the address space will be not address space, right? So address space is memory space size, that is 4 megabyte or gigabyte. This is gigabyte, no? 4 gigabyte is the page table. And the memory for page table alone is what? Is 4 kilobyte? No, page size, you know. Oh, he's asking you, okay. Maybe I should improve this slide, make you understand very clearly. Okay, no problem. Good, good. Each, like let's take a page table. Page table entry is 4 bytes. Frame number is 4 bytes. Like 32 bits. Okay. 32 bits is the frame number, right? And offset is 4 kilobyte. 2 to the power of 12. Okay. So 2 to the power of 12 and 2 to the power of 32. So what is the physical address space? Can anyone tell me, please? 2 to the power of 44, no?
Yeah.
Yeah?
Yeah.
Because 12 bits for the offset and 32 bits for the, if you want to put them properly. So you will put the, frame number first and the offset next. 2 to the power of 12. Add them together. So 2 to the power of 44. Either RAM size is 0 to 2 to the power of 44 minus 1, which is equal to 2 to the power of 44 bytes. So that is the RAM size. Okay. So you require logical address space is 32 bit logical addresses. So you consider this 2 to the power of 32. Okay. So divide by 2 to the power of 12 equal to 2 to the power of 20. So number of pages, right? Is it not 2 to the power of 20? Hello? I think
Yes.
is incorrect. Number of frames required is 2 to the power of 20, no? Is not 2 to the power of 1024. Is it not 2 to the power of 20? 2 to the power of 20 is, is not 1024.
Should be 2048.
No. How can 2048 is only just 2 more, right? You multiply by 2. You need to multiply by 1000, right? Isn't it?
1 megabyte.
Okay, I think it's a mistake here. I would really fix it and then repost it. Okay. It's a mistake here. If or otherwise I need to correct it. How do you correct it, sir? 4 byte, the physical address 4 bytes, page table entry is 4 bytes. Why did I write on 4 megabyte physical address space here divided by? Is it given to you? If given, 32-bit addresses you're using doesn't mean that you have to use all the physical address has to be, the RAM has to be 32-bit addresses or 44-bit address. We said that 32-bit logical addresses, I'm translating literally to, to the physical address space that we were talking about in looking at the size of this one, right? If I'm looking at this one, what are the frame numbers possible is 2 to the power of 32 number of frames, and each frame is 2 to the power of 12, and the RAM size is 2 to the power of 44. I said that. Okay. So you require to address any byte in the RAM, you require 44 bits. But you're using 64-bit operating system or 32-bit operating system. See, you know what? Right now, let's look at a scenario. You have 16 gigabyte of memory and you are using 64-bit operating system. 64-bit operating system can go to up to 16 exabytes. So 16 gigabyte is absolutely nothing compared to 16 exabytes, which means that a bigger operating system will always be able to actually, address less than this maximum possible. Maximum possible here in this case is 44-bit operating system. Okay, so you can always go less, and your 64-bit operating system is also going to support, no problem. Anything more is supposed to be no problem. Anything less is not able to work. Okay, so because if you are less, then your offset is not going to be 12 bits and your frame number is not going to be 32 bits. It's not impossible. It's not possible. So the address has to be 2 to the power of 44 in this particular case, a 44-bit operating system. Okay, so now I think I wrote down this thing in there. So you are dividing, I think, number of physical address space divided by the page table memory for the page table alone. Memory for the page table alone. Why did I write that like that? 4 bytes.
I think you're trying to say that's the minimum amount of memory in order to get the page table, not
Yeah,
including the frames and the offsets.
no, but let's like number of frames required here. So do you know the process size? Do we know the process? Okay, this is the maximum address space. Do you agree with me? Your process can technically be 2 to the power of 32 bytes. That's the process size, technically. But real process size can be less than that. Just like I told you earlier, the example here. Look at that. The maximum possible okay configuration of your process is 16,384 bytes. Okay, that's a maximum. But really here is only this. That means that keeps you some of the pages are not really used. But if it is a maximum, all pages will be used. Okay. So here, in this example, we were talking about here. Where is my process size? If we don't give the process size, I have to use this one as a process size. Do you agree with me? 32-bit logical addresses, not physical addresses. 32-bit logical address. Okay. So 4 bytes each. So 1 million entries for the page table. Okay. Oh, now I understand. Okay. So you require, I'm sorry, so I should have, looked at it before. So here, I would rewrite it. No, I'm improving it. Okay. 4 megabyte for the page table. Okay. Do you agree with me? Page table size is 4 megabyte. Yes or no? I'm going to I have to improve it myself. I have to write down and then post it to you. I can't leave it without proper explanation to you. Each look at here. I think you will understand very easily. Okay. How many entries you have in the page table? Possible.
1 million entries.
Yeah, 1 million entries. How did you get that? So the logical address is total address is this one, page size is this one. So you divide that, you get the number of entries, number of pages. So each entry is 4 bytes. Million means what? Million means mega. Do you agree with me? So that's why 4 megabyte for the page table alone. Do you agree with me? It fits in one page. Is it fits in one page? No, it doesn't fit in one page. Oh yeah, this page is correct. There is no mistake. So you require, but anyway, let me just rewrite it, because if I rewrite it, it will be a lot better for you and for me too, because when I explain, I don't want to really look for myself, and waste your time. Because you will understand if I explain clearly. And you will be lost if I don't explain clearly. So everything is fine here. So far, so good. So I'm going to rewrite it the way I'm going to rewrite it. 4 megabyte per the page table alone. Okay. So what I'm doing is I did revise it like this. You correct me if I'm not correct. 4 megabyte of memory you require for page table alone. You agree with me? This is very clear. So page
Yes.
table would have 1 million entries and each entry is 4 bytes. And that means, you require 4 megabyte for the page table alone. So if you know the page table, okay, how many pages you require for page table alone? That's so many. So it's like here, you want to load these 4 megabyte into the memory, right? Do you agree with me? How many frames do you require for the page table alone? Okay. I think I'm not correct. It's 1024, right? Isn't it? That's what is coming in. For page table alone, you require 1024. Just for the page table. It's written down very clearly, but the thing is I didn't read it properly. Let me move it this one a little bit aside. Yeah. My apologies. Okay. So the number of pages needed for page table alone, number of frames you require for page table alone, okay, is 4 megabyte divided by 4 kilobyte. Do you agree with me? I think number of pages needed is confused me because I was thinking about the process, not really like frame table, page table alone. For I wrote down there down below, but it should be upfront for page table alone. Number of frames needed for equal to 4 megabyte divided by 4 kilobyte. That's it. 1024 frames. Yeah. Is it clear now? I'll post it again. I won't really bother you with the questions in the exam, but I want you to know, okay, the subject. Exam will be a lot easier. So the number of frames needed for page table alone. Page table alone equal to needed for the page table alone. Our number of frames per page table. Needed is okay, right? Very good. At least no mistake in in the number there. 1024 is correct. So you need 1024 frames to load just the page table alone. So you need what? So to locate the frame number where you require as long as the page table is fitting in one frame, you don't need to have a second lookup or third lookup, right? You need multi lookup here. Do you agree with me? Yes or no? Save as. I'll post it right away. Otherwise, I'll forget posting it, and then you'll never get the right one. Then this lecture notes is improved every semester, though. I find something improving, and then I always improve. Okay. If you don't understand, please don't hesitate. Just catch me, because it's me too. I'm very curious and just trying to do the best detail as possible. So you know what? 4 megabyte for the page table alone. That should be loaded into frames. 4 megabyte divided by 4 kilobyte is 1 kilo. 1 kilo is 1024, which is 1024 frames you require. Good, right? So hierarchical paging you require. It's just not one page table. Your paging is multiple pages you require for the page table alone. And you know what? You want to identify the page number, you can have a hashing algorithm. Or you could use inverted page tables. There are 3 different ways of actually creating. Hierarchical means what? The outer table, inner table, next level table. I did show you earlier. An algorithm of looking at page table, outer page table, and again within that page table there's an offset. So all that is I really did right, isn't it? Okay. Okay, I'm posting it right now as we speak. I'm going to the Leah, post that material there, distributed documents and list of the document that you have here. And I want to update the document. And I want to update the document here, right? Which one is this? Memory management, which is chapter main memory algorithms are given. So this one is the one which is main memory chapter 09. I'm deleting it. Does it let me update it? I'm not sure. Main memory chapter. Main memory chapter. I think you have downloaded already. Main memory chapter 9. main memory CH09. I'm reposting again, right? Sorry for this, but you're getting better lecture notes always. There's no one direct way of getting everything clarified. So you always have to strive to improve. So go to the computer, my computer, go to the pages here. But you did not understand, please don't feel shy to ask me question. This is your class. And each time I see interesting story, it is good. Okay, I posted it now. And you should have it right there. Okay. It is posted there. And memory person. Okay, that's different ways of doing things. For example, so page number is divided into, okay, into outer, which is offset here, right? Which you look at that offset 4 kilo. Is it 4 kilobyte? Each page number is 4 kilobyte. Page size is 4 kilobyte. In the previous example, 4 kilobyte is the page number, which is 2 to the power of 12. So which means 12 bits are required for offset. And you require, what was the page number? The page number, right? So the page table is how many entries you have in the page table? 1 million entries. 2 to the power of 20. To represent 1 million, you require 20 bits. Do you agree with me? Yes or no? Hello?
Mhm.
20 bits you require. So the 20 bits, and this is 12 bits, totally 32 bits. This is the offset that represents 4 kilobyte. And you need to divide this into 2 parts, or 3 parts, or 4 parts. So how many, sir? So how many frames you have here, right? Okay. How many frames you have? 1 million. 1 million frames you require to put that in. Okay. So which means that, you require the 1 million and there you're dividing 1 million. So you will not be able to put the frame, page table alone in the thing. And then you have to identify the page table, like identify. So outer page table, inner page table. So page table 1, page table 2. So like that, you divide again into multi-level, right? Multi-level. So look at now here. So outer or inner. So if you use 32-bit operating system or 64-bit operating system, you can 64-bit operating system always is supposed to will be able to pinpoint each address of 32-bit operating system because 64-bit is bigger. So inner page is only required 10 bits. Inner page required 10 bits. Why 10 bits, sir? 1024. Okay. Hello. With 10 bits, how many pages can you locate? 1024 pages. Do you agree with me?
Yeah.
So that means, so 1024 pages is inner page, the location bits. Outer is another 10 more. So the P1, outer is here. Look at that, outer is here. Okay. So outer is here. So outer is this one. Inner is this one. Is it clearly understood or no? So 10 bits are getting from the page number here, and then again, you will be locating that into finding out the actual address, isn't it? Actual address, taking these many bits here, and again putting that together, and then putting that offset together will get you the exact address. Okay. So 2-level paging example with 1 kilobyte size. It's another example we're giving it. 1 kilobyte 2 to the power of 10. It's easier. So 32-bit machine 2 to the power of 32. 32-bit machine means RAM is 32 bits. RAM is 32-bit addresses. So 2 to the power of 32. How much memory can you have in the RAM? 4 gigabyte. Of the RAM size 4 gigabyte. Or 4 billion bytes. So the page number here, if it is 2 to the power of 10, so the number of bits for the page number or frame number, I think it's a RAM, right? Logical address. So it's a logical address is saying, not physical address. I'm sorry. 32-bit machine, I can go to 4, but the logical address is divided into 32 bits. The logical address and physical address is the same size in this case because so 32-bit machine means you can only go to 32-bit, but you can, even if you keep more than 32-bit, 4 gigabyte, it won't be able to access. So offset is 10 bits, 1 to the power of 10. So this is very clear, right? Okay, 12-bit for the page number and 10-bit for the offset. Why in the previous example, right? Isn't it? In the previous example, what was the page size? Was it 4 byte or 4 kilobyte or 1 kilobyte? It was 4 kilobyte if I remember.
4 kilobytes. 4
Yeah,
kilobyte. Or
it
memory.
is.
4 kilobytes,
Yeah.
yeah.
Yeah, 4 kilobyte. And we said that 20 bits were there for, these are 20, the page number needs 20 bits. Here the page number requires how many bits? In this example here, right? Page number, okay, is 22 bits. Because here it's, earlier it was 20 bits because it was 4 kilobyte. Now it is 2 kilobyte. So that means the 2 bits goes to the page number. So 10 bits for the offset and 22 bits for the page number. Okay, since the page number itself, page table is all again page, right? So you got to divide this into 22 bits into 2 parts again. Okay, so how many frames can you put it in one frame? How many entries, page table entries can you put in one frame? Because this is the offset. That means 10. So which means like here, look at it here. The real offset is 10 bits. So it is within what? Within the frame. Within the frame. Of the process. Okay. But what is this one, sir? This one is 22 bits. Because it's 10 bits, there will be another 10 bits here. This is the offset to find the page number. And what is this one, sir? This is 12 bits. So outer, this is the whole thing is to identify the frame number of the page there you loaded. But this one is the page table, the page table is divided. There are 2 page tables. There are 2 page tables. Outer page table is 12 bits and inner page table is 10 bits. Okay. So outer page table will find out the offset and together will find out exactly which frame number you should take. And then you go there and then put that in, plug it in, and you get exactly this. You understand me, right? This is a mapping table. Okay. This is the outer page table, and then this is the offset to identify the page table. Because even though you are dividing into logically outer page table, inner page table, they are not like that. They're all put in the in the memory, which mean that, so this one is going to identify the page number where you need to go. And within that, okay, these bits are going to find out exactly which entry you need to take. That is the frame number. And go to that frame number and put offset to it. And you get the address. You understand me? Is it clear? Yes or no? Page table is loaded into the memory. Okay. Page table is loaded into the memory, right? So these 12 bits, here, right, is identifying the page number. And this 10 bits is identifying offset within that. This is page table. And what you get here is a frame number. And you take the frame number and go to and add that offset to the, and then you get the physical address. Okay. So look at this, exactly giving you the same thing. So these bits, P bits, is to identify the entry number. And put together with the offset, which is this one, will identify this one. And this is the actual frame number where you actually look at. So remember, I can draw the figure again earlier. Earlier, I draw the figure like this. Okay. To identify, there's a P1 bits. Identify the frame number. Okay. And within that P2 bit is going to identify this one. So this one. So this one is this one. And this one, this entry here is this one. And then the content of that is this one. This is offset within the page. And then you replace and you get the frame number. And that is the physical address location. I know it's a little complicated, but it's not. At least you are introduced to this concept, and you will be able to do it well. In future, when you have to review the same topic with another advanced course, then you will be able to do it very well. 64-bit logic is the same story. All that you need to put in is 42. If you need inner, outer again, so 10 more bits and 10 more bits and 10 more bits like that till the last one is going to be the concrete number, which need not be 10. You see, offset, keep on going, take the page number and go back again and things like that, right? So 64-bit logical address, See, look at here. If you go more and more and more and more, you're going to add 10 more, 10 more, 10 more like that. This is a huge search. You can divide that again into 2 more searches. So hashed pages is probably the faster way of doing it. Okay. Did you study hashing in any algorithms, data structures course? No?
No.
No.
So you have a hash key, for example, right? So what you do is, did you study ISAM, index sequential access memory?
No.
Index sequential access memory. So there's a file system. File system, right? You studied file system, no?
No.
Sequential files, random files, index sequential files, and databases. So this is the way you organize bits into bytes, bytes into rows or records, records into files, files can be a different type of file, which could be a sequential file where you need to read it sequence. If I have to read this particular one, I have to read all of it and then try to figure it. So that is a sequential access. Random access will have all the records written down here. Okay. But there is a number also written down here, or where it is loaded is also written down. So you will be able to access it. First of all, identify the location. To identify where the byte is, the record is located. This is random access, index. So index sequential file is like ISAM file. Okay. Random access is one thing, is a key. Based on the key you access. Index sequential is you can use a hashing algorithm where you find the index by hashing. There is a hash key. Okay. So you hash with the key. So the lookup search number you want to really, I want to identify the, record 5 or something. So hash with it. And then you get another number. And you go to that number and search it, you will directly get it. You don't need to read, one after another. But only thing is when you have duplicates, for example. So when you hash, you get the same number. Then you have to search sequentially after that. So somebody is going to teach you that because it's a little bit more explanation needed to that. Hashing, hash key you will use, right? Hash function you use. All that you're doing is identifying the frame number. So this sequence, remember I said that? You did that? Why, sir? Because the hash key are matching exactly the same result you're getting. Okay, same result you're getting. And then that must be kept in sequence. Again, this is a linked list. This is the next pointer. Most of the time it is single though. Most of the time, single. If your hash key is good, that means it's going to be single. The bigger the hash key, is more chance for you get the single. Single means hit directly. It's a direct hit and just get it. Okay, linked list. Somebody teach you linked list or no? No?
No.
So I will teach you array list maybe I'll teach you hashing. If you do very good in the next course or something, I will teach you more. This course, I already taught you more than the previous things. I demos and all. I didn't do those many demos to the other sections because I hardly did 2 or 3 demos. I think 5 assignments and 2-3 demonstrations I did. But now I did a lot more demonstrations. In future, I think I'll even do more demonstrations. If I have more time, I'll do that more demonstrations also. Inverted table is another way of really doing lookup. All that is basically to find out the frame number. Okay. So inverted table. All right. So inverted table ID, process ID and so on. So I think I'll leave it, I'll leave it at this point of time because the remaining thing is segmentation. I was not teaching this, So this chapter, only up to this point I was teaching. I left it to let you see it. Okay. I stop it at this point of time. All right. You want to do a TKP or is okay for today? It's up to you.
If we can talk about the midterm, how
Yeah.
it will be.
That's a good idea. So let me go to that's a very good idea. Okay. Give me 1 second. I'll tell you the type of questions, and then at least you will be preparing for those questions. Exam is going to be easy. That's for sure. You should be doing well. Okay, if you prepare though, if you prepare without preparing, you come. Obviously, it's going to be difficult. We have 6 quizzes done. 7th quiz. I can give you a 7th quiz if you want. The 7th quiz. Should be easy, but yeah, this was a previous chapter. I don't know why I give this now. So maybe I was teaching something else before. Anyway. The midterm exam. Shortest job first algorithm. Okay. Shortest job first algorithm is going to be there in the exam. Okay. Is it clear? Shortest
Yes.
job algorithm is one question, and the round robin method is another question. So I'm going to tell you the big questions, okay? Small questions, you can always, multiple choice questions, you can always answer them, right? So round robin method, shared buffer is another question, shared buffer, all right? And the shortest remaining time first algorithm is also another question. First come, first serve is another question. So those are the questions for the scheduling algorithms. Remaining are multiple choice questions. The total number of questions are 45 and the total score is 50. And there are multiple choice questions, you know, so you'll be able to answer them. If you don't, I will raise the, you know, the grades to the level, respectable level by adding or adjusting. You understand me? The highest grade is not enough, right? Satisfactory. I can increase the highest grade by certain number of points, and then everyone gets the same number of points. You understand me? For example,
Yes.
I can add 5 points to all of you. If the highest is like 45 or something, then I can add 5 points to everyone. If the highest is 40, for example, maybe I can still add maybe 7 points or 7. It all depends on the average and so on, okay? I will keep the average to the respectable level, like 75% or 78 or 80 or something, 80% average. You understand me?
Yeah,
Yes.
it will be up to today or the.
Oh, that I can't really just read everything, you know. I won't really define that. You read as much as you can. Obviously, the first chapters, right? Isn't it? Differentiating that is where to stop. You know, study everything. You know, because the following exam is final exam in 1 week. I would like you to study everything. The last chapter, memory management, is not needed. Okay.
So Tyler, do you recommend just going through the class notes or?
Yeah, you don't need this chapter 6, right? Chapter 9, but you go to the previous chapters. You go to them, you know, as much as you can cover, you know. But this is scheduling algorithms, right? CPU scheduling. It is there throughout the, so this only just leaves you four more chapters. These are 4 chapters. This one I've been teaching right from the beginning anyway. So 6 is not included. So teach 5, read 5 of them. And the following exam will be easier for you if you study them now. And this is the only thing you need to read, right? And then probably 1 or 2 commands, and that's it. Yeah, is okay. I told you the most important questions are, like, for example, the questions I told you now, right? 1, 2, 3.
Sir, is the midterm on TIC FP?
Yeah.
Okay.
10 points I already gave you out of 40, 50. I already told you the questions to concentrate. 10 points out of the 50. 50 points. That means 10 points means 20% of the grade is already known to you what the exact questions are. And these are the only questions people who are making mistakes. So that's why I'm telling you in advance, because it's a pity if someone makes a mistake on those questions, right? On those questions. 1 second, I'll tell you. Okay. Oh, I increase the grades there. Decrease. Okay, all right. So shortage job. I will increase the weight to those ones. Okay. Shortage job first. I only put 2 points. I can put 4 points if you want.
Sorry.
Let's make it a different way. Okay. I'm just telling you again.
Teacher,
Shortage job. Yeah, go ahead.
can you just tell us like how many questions will the?
Yeah, that's what I was telling earlier, right? I was saying 45 questions and 50 points, but now I'm saying 40 questions and 50 points.
Okay.
And then I actually can reduce the number of questions and increase the, the weight of the questions which I told you. So which is shortest job first, I'll put 4 points. Round robin, 4 points. And then shortest remaining time first is 4 points. And first come first serve is 2 points. That gives you more points. Okay. And then the remaining questions are the multiple choice questions. So if you get good grade in these 4 questions, this is where people were making mistakes. Okay. And 40 questions, 50 points.
Buffer question.
Buffer, I removed it.
Okay.
Unless you want me to keep it.
No, it's okay if you remove.
Yeah,
I don't-
I'll keep it in the final.
Yeah.
Okay. So first, so that's it. So 40 questions, 50 points. And I told you the questions already. Remaining questions are multiple choice question. I can't tell you. This is not TKP, quiz class participation. It's a final midterm exam, right? So that's why. Okay. Is it clear?
Yep, it's clear.
Let me just do it again.
Sorry.
1 second. Just looking at myself. Yeah, 40 questions, 50 points. Yeah, what was it? Okay, what is the question?
The exam gonna start at 30.
Let's start at 10:30 or something. What time you want to start? I'll open, but I will not really ready by start. I'll start at 9 or 9:30 or something. Because if someone is late, 5 minutes, I will not really bother. You
No,
understand?
just this is my question. I don't have any idea.
Yeah, that's what my answer is. 8:30 is too sharp, right?
Sir, what is the duration of the exam, sir?
Duration of exam. 1 second. Duration of the exam. So we'll have a class after that or something. Okay. Because I want to finish off everything, by next week. And then after that, we can leave it, so. I can give you 1 hour, 15 minutes. 75. Yeah, 1 hour, 15 minutes, 75 minutes.
And just to be sure, the exam is on chapters 1 to 5.
Yeah.
And 7 and 8. Is that right?
Yeah, basically what you have, I told you, I think, let me go here. I think we have the TKP. Yeah, you will look at here. It's the one right here. Look at that. So this is the chapter 1 to, this is chapter 1, right? chapter 2, chapter 3, chapter 4, chapter 5. I think, is it chapter 5? Yeah, chapter 5. So, and then that's it. Chapter 5. That's the only thing. First 5 chapters.
Okay, thank you.
And the scheduling algorithms I did teach you on the way, right? So, and I told you what I'm giving you a question. So follow those questions carefully, right? Okay,
Okay.
those algorithms, you just don't make mistakes. And again, when you are writing the answer, if the answer is 2, don't put 2.0. 2 is 2. If I tell you the decimal places, you just respect it. You have to put, because the computer is going to grade your
Score.
answer. Yeah. Which means that you put in, instead of putting 2, you put a 2.0, you may not take it. If you want to, you need to put 2.0 and you put 2, you won't take it either. So I won't go back again and check everybody's thing and then try to correct it. No. Don't make mistake, read question carefully. Question tells you whether the answer requires a decimal place, it will tell you. The question tells you how to answer. Because it will be automatic, number, you have to enter the number. Okay, when you get this, CT, PT. Who is that actually speaking, Kesara?
Yes, sir, it was me.
Where are you actually? Are
I'm
you at
home,
home?
sir. Yes, sir.
Okay, all right. Okay, all right. No, anyone has any other questions? No, we'll decide upon. The exam starts at 9 o'clock or something, and Okay,
Oh, so we log in at 9?
you will all get it 9, yes, at the same time, all of you. Decide upon when to get it right. So we'll decide upon.
Okay,
So
sir.
0, 1, 2, 2. So 0, 1. Tomorrow is Wednesday, right? Is it not? It
Tomorrow
is
is
when
Tuesday.
no, it is Tuesday. Tomorrow is
Tuesday.
Tuesday. Is when Wednesday, April 6, April 5, I think, right?
Yes.
So 9 a.m. So don't come late. Okay. So 0, 1, 2, 2. Okay. Advanced settings. Only start time. Complete. That's it. Okay, I will go to the tests and try to find out. There. Fine. Okay, I'll set up the time there. So 1 second, I will send all of you a message because I don't want anybody it's absent today should not be penalized. So compose a message to all students. So what is it actually? This is yeah, midterm exam on Wednesday, right? This week. Hi all. I will open the, at 9 a.m. 8:30 a.m. I will open just like 8:35 or 8:30 or something like that. So I'll take the attendance and everything will be done by 9, and then I'll be able to release the thing. And if you have any question, right, I can answer that also. And That's it. So let me send the message to you and you confirm to me that I sent it to you. Students from my class, which is operating systems class. All of you will get a copy of it. I sent you the message. Can you please confirm that you received the copy in Mio?
Yes.
You got it, right?
Yep, got the message.
Good. So at least it's from my side, it's clear. Okay, I think I'll leave you there for today. Enjoy your day, and that's it for the day.
Thank you.
Thank
Thank
you,
Welcome.
sir.
Enjoy
Thanks a
your
lot.
day.
Nice afternoon, sir.
Welcome. You too. Thank you, Anna. Thank you.
Thank you.
Thank you, sir.
Thank
Have
you.
a good afternoon.
You too.
Thank you,
Thank you.
Professor.
Thank you. Thank you.
Good day, sir.
Good luck to you. Good luck to all of you. Enjoy your time.